Welcome back, everyone. In order to understand the concept of displacement, we need to precisely define what is position. So if it is one-dimensional motion, we could mark the positions by saying that an object is, let's say, 2 units towards the right of origin. Or we could say that the object is 3 units to the left of the origin. So for one-dimensional motion, position could be defined by using a number line. That was one of the ways to define position. For 2D motion or motion in a plane, we could define the position or we could quantify the position by using Cartesian coordinate system. So we had two axes instead for 2D motion. This was the y-axis, this was the x-axis, and if there is an object here, we figured out what is its x coordinate, what is its y coordinate, and we would know where that object is located. X and y coordinates are definitely one of the ways to represent position of an object. We are going to get introduced to a new way of representing position. It's called a vector. So let's see what is a vector. The most fundamental kind of vector is the position vector. A position vector is a vector that defines the position of an object. If we take the case of two-dimensional motion, the position of any object can be defined by, let's say, x coordinate, y coordinate. This position can also be defined by using a diagram. So we use a ray. The ray originates from the origin and ends at the position of the object. So ray, this ray represents the vector. This ray also uniquely identifies the position of the object. The coordinates of a point is definitely one of the ways to locate a point, to locate an object. A vector is another way to locate an object. If we take the example of two-dimensional motion, that is motion in a plane, let's say the object moved from place A to place A, and took a path and moved to place B. Place A's coordinate was x1, y1. Place B's coordinate was x2, y2. So definitely x1, y1 and x2, y2 gives us the position. We are going to look at one more way of representing the position, that is vectors. Vectors is diagrammatically represented by a ray. A ray joining a ray starting from the origin or the reference and ending at the object itself. So this ray OA, is the position. It indicates the position of point A, whereas the ray OB represents the position of point B, represents the position of point B or object B. Now these rays are called position vectors. Position vector. Okay. A similar example has been given here for a 3D case. Here, instead of just two axes, we have three axes: the x-axis, the y-axis, and the z-axis. A ray can be in a plane, it can be aligned in a 3D space also, right? So here also, this R1 ray is the position vector of point A. It's the position vector of this point. Whereas R2, R2 vector or this ray is the position vector of point B. So we understand what is position. Position is just the location on any grid, on a graph paper, on a 2D plane, on a 3D space, Cartesian coordinate system, or on a straight line, depending on whether the motion is 2D, 3D, or 1D. So we understand how to quantify position now. Now we move on to understanding displacement. As you can see, the object has actually moved from position A to position B. That means the object has displaced. The object can move from point A to point B using many different ways, many different paths. One of the paths is shown by the red arrow here. Let me draw a few more paths. The object can also go around, let's say, this path and come to point B, or the object could have moved along this path and came to B, or this path, or this path, many different ways to come to point B. But the displacement is the same in all the cases because displacement is defined as the difference between the final position and the initial position. It doesn't matter which path, how longer or shorter a path we took. If the final position and the initial position are identical for four different cases, the displacement is going to be same for all those four different cases. Diagrammatically, displacement, which is also a vector, is represented by the difference of final and initial position vectors. Let's look at it. So we all understand that R2 is the final position vector, remember, and R1 is the initial position vector. Now, displacement vector, let's call it delta R, the displacement vector. This is defined as final position vector minus the initial position vector, R2 minus R1, the final minus initial position vector. R2 minus R1 is also a vector which is represented by this, starting from R1 and ending at R2. So this is the vector delta R, the displacement vector. Now, if you have studied vectors before, try to figure out if I give you a vector A and then I give you a vector B, how would vector B minus A look like? You can use either the triangle law or the parallelogram law to figure this out. The answer is this. You would find that this vector would be represented by this line, this blue line that I'm drawing. Okay, just try this exercise on your own and then you would understand why delta R vector is a vector starting from A and ending at B. Why this is delta R vector. So a quick recap of what we did here. We understood how positions are represented using vectors. Those are called position vectors. Position vectors. Using position vectors, we defined something called displacement vectors. Displacement in essence is basically the shortest distance between 2 points, the initial and the final one. Now, let's look at distance. Distance is simply the total path length. What is distance? So let's say that is using this path 1, the object moved from point A to point B. Then using this very short path, path B, path 2, the object moved from point A to point B. Then using a third path like this, the object moved from point A to point B. In all the three cases, the distances covered or the total path length is different. Distance is the total path length. So it actually depends on which path you take. If you take path 2, if you take this path, the distance is the smallest. And if you take path 3, the distance is the biggest, right? So distance basically is the total path length. Now, one thing you would observe that the magnitude of displacement remember, that means the numerical value without considering the direction. So the magnitude of displacement for this motion from A to B, irrespective of which path you take, is always going to be the length of path 2. Length of path 2. Is it not? Because that's how displacement was defined. Displacement was the magnitude of displacement was the shortest distance between 2 points. So the shortest distance between the 2 points is traced by this path 2. So that length is the magnitude of displacement, remember. To give the entire information about displacement, we need two things. One is the magnitude and the other is the direction. Whether it's going from left to right or right to left, that is also important. The distinction is also clear. Let's try a few questions on this. So take your time, pause the video for a minute, attempt the question, and then come back to look at the solution. Let's take a look now. A person walks along a semicircular path from A to B. So this is the initial position, and this is the final position. The path is also given to us. The person took a semicircular path. So this path was taken, the red path, okay, from A towards B. What we have to find is the distance and the magnitude of displacement, not the direction of displacement, just the magnitude is sufficient. Well, the distance is actually the total path length. So you tell me what is the total path length of this of this semicircular path. It's half the circumference of this circle, right? So distance is going to be 2 pi r upon 2. So distance is equal to just pi into r. What about the magnitude of displacement? The magnitude of displacement is the distance of the shortest path. So this distance, AB. So displacement is the length of path AB, which is 2 times r, since this is r and this is also r. So 2r. Distance is pi r and displacement is 2r. Now think about this. Can the magnitude of displacement ever be more than the distance? Think about it, okay? And let's move on to the next question. We'll do this question and then we'll move on to the new concept. Again, pause the video, attempt it once, and then unpause and look at the solution. Let's go through the question. If position of object change with time as this equation, the variation of x with respect to time is given to us, fine. Then find the net displacement of the object in time interval t equal to 1 second and t equal to 4 seconds. See, this is 1D motion, remember. If x is equal to t square plus 4t plus 5, you tell me what is the value of x at t equal to 1 second. To do that, you'll have to substitute 1 in place of t. So this is the expression that we are referring. So we'll write 1 square plus 4 into 1 plus 5, 10. X at 1 second is 10. So that means if you draw the position of the object on the number line and this is the origin, you would find that the object is somewhere here, plus 10 at time t equal to 1 seconds. Let us see where is the object at t equal to 4 seconds then. What is x at t equal to 4 seconds? So now instead of 1 everywhere, you put 4 everywhere. That would give you 4 square plus 4 into 4 plus 5. That is 32 plus 5, which is 37. In 4 seconds, it's going to go further towards the right at plus 37, t equal to 4 seconds. If you know the final position of the object and you know the initial position of the object, can you find the displacement? Can you find the net displacement? It's easy to find, right? The net displacement is given by, or delta R was given by RF minus Ri. If this is one-dimensional motion, then you could simply write it as 37 minus 10, that's 27. 27 units, can be meter, centimeter, whatever is given in the question. Delta X is 27. That's the answer. Let's move on to the next concept, which is speed and velocity.